Well, hello friends. Welcome back to the program. Today we are going to play another round of FIXME Roulette, which is the game where we get grep for FIXME or to do in the Serenity codebase, and then we grab one random item and then work on it. We're just going to make sure that we grep like this, so we get line numbers and case insensitive, and we will be choosing from 5,505 FIXMEs, so quite the selection. And we'll let Chef do the actual selection. So here goes. Okay, UserspaceEmulator soft CPU. Push CS to do instruction. Oh, I see. So this is an unimplemented instruction in our UserSpace X86 emulator on line 2411. Cool. Push CS. Okay. I have not touched the UserSpace emulator in a while. So this will be good to get back to that. Also, why do you think this does not belong to the project target? Oh, because, right. So Userspace emulator only builds on X86. It doesn't build on 64-bit yet because we haven't ported the emulation stuff to 64-bit. So I guess I need to, for CMake to, or for CLine to understand this correctly, I probably need to switch to the i686 thing and then just swap things over like this. I think that's probably okay. I'm just going to do that. And then we'll see if it can pick everything up. Seems like maybe it could. Cool. Yeah, so that's actually very fortunate because normally I don't even have a 32-bit build, but I've been working on this new string class, as I mentioned yesterday in the car talk. And because of that, I had to build on 32-bit to get everything working. And I have a fresh 32-bit build, thankfully. So let's see. So, okay, so we need to implement the push CS instruction. I have to reorient myself. It's been a while since we were here. So let's see. Let's see if the thing even still works. I haven't run the UserSpace emulator in forever. But yeah, so when we implemented that, we left, or when I initially implemented it, I left a whole bunch of things unimplemented, and then other people have helped out and by adding stuff like FPU support and some limited vector instruction stuff. Like I know Leon has worked a bunch on it. And let's see, so UE, bin ID, okay, it still works, still capable of running a program. So if you are not familiar with UE or UserSpace emulator, it is an x86 emulator, like complete CPU emulator for user mode code. So it only runs Ring 3 code, and it basically emulates the CPU running Serenity programs, and then we can instrument the instructions to do stuff like look for memory leaks or invalid memory accesses, stuff like that. And we do that by sort of instrumenting the memory accesses. So when you do a memory access at the instruction level, we look, hey, wait a minute, is this memory access into a piece of malloc memory that was recently freed, stuff like that. Anyway, all that to say, we need to implement some instruction here. So push CS is a push code segment. So just going to look at surrounding code here. So push 16. I don't know if we even have segments actually. I think since it only ever runs user mode code, I don't think we implemented anything regarding segmentation CS, but we do have a concept of CS. Okay. So it has segments. So we can just Maybe we can just push 16 CS like that. But probably it needs to be a value with shadow. Right. So we need shadow bits as well. The shadow bits are, we use them to keep track of whether or not memory is initialized. So when you allocate a stack variable, for example, and you don't initialize it, then UE marks that, or all memory is initially marked as uninitialized. So every byte has a corresponding shadow byte, basically, that keeps track of stuff like that. And I think here we need to initialize what we're pushing to the stack needs to also have a shadow byte, or 2 shadow bytes, since it's 16 bits. But I think we should consider whatever's in the CS register, we should consider it to be initialized. That seems totally reasonable, because the system wouldn't function if you had a bogus CS value, because that's the segment that you're executing code from right very now. So shadow wrap is initialized. Yeah, I think that's the one that we're looking for. Would that just work? I mean, I guess the first thing we should do before all of this is to actually write a test program that fails. So let's see. We'll call it push CS. Wow, what an exciting name. And then we will add it to the CMake list here, push CS. All right. Okay, so how do we test something like this? We need to have, I mean, the easiest way to test it is to push CS and then read it back from the stack and then see and just print out what we get, right? That would be moderately interesting. So it would be a way to find out what the current code segment is. So let's do something like get CS, maybe. Yeah, we don't need. Okay, and then how do we do this? Assembly. So we need to push CS, and then we need to pop EAX, I guess. And then, oh my goodness, I have not done this for a while. That's how you do an output, I think. Okay, let's hope that's correct. Otherwise, we have to look it up. But we have examples in our own code base, actually, we could look at, but it's probably okay. So this is going to be a 16-bit value. And we'll just print out get CS. Yeah, I guess we can do some of the others too. In fact, you know, we should probably implement all of the different push segment register things, because why not? So there would be 5 of them. So C, D, E, F, G. And yeah. Not the most riveting editing right here, perhaps, but should I have done that with a macro? Whatever. I mean, I guess I should have checked that it compiles first of all, because otherwise I have to edit all of these, but I'm feeling confident for some reason. Okay, let's try to build this. Push CS. Would you link? Why is it getting stuck? Okay, well, it eventually built. So let's see if that program will run at least natively inside Serenity. And then we can check that it fails in UserspaceEmulator. So let's see. So the values look a bit goofy. These should be 16-bit quantities, actually. So I guess we have junk on the stack. I think when it comes to pushing segment registers are 16-bit, but the stack is always aligned to the current machine word size. So if you're in 32-bit mode, stack will always go in increments of 32 bits, even if you're pushing a 16-bit quantity. So I think that's why you see like garbage here, but it's really the bottom bits that are relevant. So we should be truncating those, actually. So I guess we'll just do this. There we go. But it's looking optimistic, though, that at least we can run the thing natively. Yeah, and these values look perfectly correct. Those are the various segment, what is it called? Segment selectors that I would expect. It's been so long since I did low-level Intel stuff. So this is good, actually. It's healthy for me. So let's try to run it with UE. Unimplemented instruction, push CS, as expected. Right, so that would be this instruction right here. So let's just see if it works, if we just take all of these fellows and then pack them out like this. Wouldn't that be cool if we just got this working? Yeah, I really need to actually go and look at 64-bit support in the libx86 and UserspaceEmulator, especially now that we've been talking more and more about abandoning the 32-bit support and going full 64-bit. It means that like we will. I don't want to leave the UserspaceEmulator behind because it's a really cool piece of tech that can do nifty things, but it's gonna require some finessing to get it executing 64-bit instructions. I mean, it's not complicated. It's just a bunch of implementing 64-bit versions of instructions. Why don't I have FS and GS though? I only have. Oh, I forgot about SS. Oh my goodness, forgot about a good old stack segment. See, I am very rusty apparently. So get SS. Right. Wait, is push SS a thing? It is a thing. Okay. Push 16, shadow wrap as initialized, SS. So we have SS in UserspaceEmulator, but we don't even have the concept of FS and GS. That's kind of strange. They're here though. We just don't have convenience accessors for them, I guess. We can add that then, that's no big deal. So fuzz and juzz, all right. Okay, see how this fares. Oh. Hey, okay. It did something. It's showing it looks like vaguely sensible things. So the environment is slightly different when you're running in UE. So apparently FS is 0 in UE. Maybe we just set it up that way. I wonder why. Where do we even set these things up, I wonder? So like hex2b, for example, or who sets these up? Oh, they're just hard-coded here. Okay. Right, they're hard-coded in the soft CPU constructor. So I think just in the interest of having uniformity between the native execution environment and the emulated execution environment, it seems reasonable that we would say FS is 23 as well, right? Yeah, let's just do that. Okay. So that's also a nice fix. So it actually takes care of a bunch of to-dos, right? Because we did all the other segment registers as well. Push CS. Yeah, so that's 1, 2, 3, 4, 5, 6 with SS. Very cool. Why is it taking so long to build? Right. I think the soft CPU, the UserspaceEmulator is like very aggressive with inlining, but it's like we're inlining a whole bunch of stuff because it turned out to be quite helpful in getting it to run faster. And running stuff through the UE, especially like heavier stuff like file manager or something like that, it's not exactly super fast. As you can see, it takes a while to start up, but it does eventually start up. And it's pretty cool that it's running in a completely emulated CPU that does every instruction like this. But yeah, it is a bit laggy. There are definitely ways we could make it faster, but don't think we've been thinking about it much for a while. It's nice to pick it back up, actually. Seems like our back traces are a bit broken here. Missing the names of various things. Bunch of broken windows in our operating system neighborhood. Anyway, let's not get distracted though. So we got this working. That's fantastic. Let's go ahead and make commits. So we'll make that first change here, just initializing the FS register. So UserspaceEmulator, initialize the FS segment to on startup. Set it to hard code it. Well, it's not hard coded because I guess we could let you change it, but wait, I'm not even sure if you can change segments as a user, actually. I have to look in the manual. Where is my Intel PDF? Do I not have that anymore? Okay, let's just download it. That might have been, no, that's the right thing. I was thinking that might have been a little optimistic, but seems like right-click Save As actually worked on that thing. This is not what I expected to open. Oh, still downloading. Okay, I am very smart. Here we go. Right. So I was looking for, I guess I want to know if you can change, well, can you change the segment register as a user? So mov into segment register. Mov segment, move an RM16 to segment register. Yeah. Okay. GP. Okay, so it seems like you should be allowed to load a valid thing into the register. Yeah, yep. So I guess we can implement that. Maybe we already do, and I'm just no, we don't implement it yet. Okay. Well, we could. You know, the easy way to test it, of course, would be to just try to do it natively and see what happens. So we'll just set fs to, I mean, it has to be a valid thing. So we had, what were they? They were like 2B into something else. Okay, I forget what they were. Let's look again. But I remember there was like 23 and 2B or something like that. So we know that at least those two are valid. So we should be able to set fs to 2B, and if that works, then we know that it's okay. Yeah. Okay. So then asm mov can't put a constant here, but we could do like this, right? To fs, and then it's an input, so it's like that. Why do I have to say it like that? Right, first outputs, then inputs. Yeah, maybe this will work. We will soon find out. I mean, we would find out if I would actually log afterwards what it became. Then I will find out. That didn't do what I thought it would. Huh. Wait, why would that? Now I'm wondering if this actually does anything. Can I disasm it? Set. We don't have search in our less? What? Okay, I'm gonna disasm it outside. Obj. Oh my goodness, I have to remember all these things. DCM Intel. Like that. FS. Okay, mov EAX to B, mov FS EAX. So we do that. But FS is not changed? What? I am confused. So is it a... Well, we're not getting any kind of crash or anything, so there's no exception happening. I mean, we should be able to set it to 0 at least. Like if we set it to a null selector, is that okay? According to the manual? If it's loaded with a null selector, then just assign it. Yeah, exactly. So that should be fine. The only thing you can't load with null is CS or SS, but all the other registers, you should be allowed to put a null selector in them. I think. Okay. Still 23 at the end. Oh, wait. I wonder if these things are being reordered or something. Now I'm getting paranoid here. Because I'm not saying... Like, it has no way of knowing that... that FS is changing from this. I don't think that the compiler sees that. It knows about FS, the FS local here, but I don't think it knows about the segment register. So maybe it's getting optimized out. Yes, it was. Okay. Right. that made more sense. Okay, so the optimizer in the compiler was just didn't understand that I was modifying the segment register, so it thought it could just reorder stuff, I guess. Okay. Great. Then we can make sure to implement this also in in UserspaceEmulator. But let's get back on track. So I was writing a thing here. So yeah, so set it to, what am I setting it to? I already forgot. I'm just setting it to 23, which matches the native setting. Matching the normal value in native execution. Typical, or the initial value in native process. Yeah. Okay, and then add accessors for FS and GS. Add soft CPU getters for FS and GS. And then implement push CS, DS, ES, FS, GS, and SS. Push CS, DS, ES, FS, GS. Where do we put SS? At the end, maybe. Yes. Yeah. You can now push segment registers on the stack. Cool. Let's allow you to change them as well. So, oh, right, we can test that easily because it shouldn't be possible to run this in UE anymore. It will fail because you're trying to mov into a segment register. So let's implement that. Mov seg RM32. So that's this thing right here. And by the way, since I was touching these lines, I should have fixed up the formatting actually. would have been the right thing to do. So let's be good boys and do that before continuing. Make sure it's in the previous commit, since we were touching the lines anyway. That's definitely the good boy thing to do. Yes, yes, no. Amend. All right, now mauve seg rm32. Okay, so I think here we have to, I don't remember exactly how this stuff works, but I know that rm32 means that the instruction has some kind of memory or register reference encoded in it. So we can extract that by asking for the memory, or I forget what mod RM stands for, but it's a memory or register reference at least. And I guess we want to read 32. Does that make sense? Because we only need 16 bits. Mauve seg. It didn't say. What does it say here? When executing mauve regstreg. Oh, we also have mauve. Mauve something seg. Mauve rm16 seg. I guess we could implement that as well. Okay, let's just do a couple more. We'll see what we figure out. So what do I get from this thing? How do I read from it? Pass in the CPU, so this, and the instruction. All right, I can do that. So the value is that, I guess, and that gives me a value with shadow, I take it. Yeah, value with shadow, okay. And then I'm supposed to validate it. I mean, the simple approach. How do I know which segment this is, by the way? Segment register. Okay, yeah, so the instruction has a segment register encoded, sure. So we should be able to do something like M segment. I think this is okay. Do we have something like set segment? Does anybody set segments? Nobody's really setting the segments. All right, fair enough. We'll just do 2 underlying. And we just want the value. Okay, by the way, something that came up in the comments after the video I posted yesterday was that I've been having this rule that I'm not allowed to add new FIXMEs, which makes sense in some ways, but at the same time, it also creates potentially this impossible endless loop in the video where I'm sort of unable to make good progress on something because I'm forced to take on like new tasks all the time. So it's like this endless cascade of tasks, and that's nice to a point. But I think we have to change the rule so that it's okay for me to add FIXMEs, because the point of the video format is to make progress on FIXMEs, right? It's not necessarily to fix them, because I'm not going to be able to fix everything. And in the process of fixing something, it's going to make sense to add new FIXMEs. So the new FIXMEs will be less work than the initial FIXME, but still some remaining tasks. And the reason I say that is because I think here I'm going to want to FIXME for like validate the segment. Validate the segment selector and raise exception if necessary or something like that. Because if I go down that hole, I think then I would have to add infrastructure for raising exceptions and things. At the moment, I don't think we have anything clean for that. But yeah. So I think yeah, we're changing that rule so that it's okay to add new FIXMEs, but we have to do something about the original one so that it improves somehow. I guess, yeah, maybe that's a better way to say it. Like the original FIXME or to-do that we hit with the shuffle needs to at least have changed by the end of the video. So it can't be still there looking exactly the same, because then we haven't made progress on it. In this case, though, in this video, the original FIXME is gone, or the original to-do thing. Okay, so let's see if this works. Could validate it, and we're also not looking at the uninitialized bits. So if you're moving like uninitialized data into a segment register, that's, I would argue that's like going to be a bug. Even though a native CPU wouldn't complain about that, because the native CPU has no concept of uninitialized data. We have, so we could flag such situations, but in a sense, that's part of validation, but like I'll add a separate FIXME for that as well. Complain if uninitialized data is moved into a segment register. Hey, it worked. That's pretty cool. Yeah, so it prints 0 because it set it correctly. So very fantastic. Okay, so let's have that. UserspaceEmulator. Implement mov seg rm32. This allows hosted programs to write to segment registers. Cool. Yeah. And there was another way to, I'm kind of ignoring the 16-bit variant right now, but there was the mov rm16 seg, was that it? So how would you get an instruction like that? So there would be like, instead of wait, mov rm16 seg. Oh yeah, the order is backwards. So we're using Intel order for these, and then I'm writing assembly in AT&T syntax, which has the order of destination and source reversed. So this moves the value of a segment register into an ARM16. So set. I guess we will try an alternate variant here. Mov. Wait, what am I trying to do? I'm trying to get GS in a different way. Okay, let's try it. So I have to move a 16-bit thing. So it would be something like this. Would that work? Expected. Oh, yeah, of course. The syntax for the inputs and outputs for inline assembly, like I know some of how it works, and then the rest is like mutations until it compiles. I never really bothered to learn all about them. I just know the basics of how to set them up. Let's see. Get GS alternate. Oh, right, we need to actually call it. Maybe we can print here alternate method of getting, see what we get. Okay. Oh, wait, that's not how you do that. I was mixing the printf syntax and our own formatting syntax. GS23 and 2B here. Oh, because I put FS, not GS. All right, my mistake. It's probably good then. It's probably good. But then we can test that this actually fails UE because it doesn't support that instruction. So that's fine. And that fails movarm16 seg. Right. So let's implement that instruction. Which we do by saying mod rm write 16 m segment to underlying instructions segment register let's see, if I write 16 and then we can shadow wrap as initialized, I guess. Yeah. So we don't carry shadow bits in the segment registers. I think that's okay. Oh, and we need to pass in some more params here. Okay. This looks vaguely sensible though. Just writing a 16-bit quantity into a 16-bit memory or register reference with the data from the segment registers referenced by the instruction. Yup. Seems good. So the thing here, by the way, the instruction segment register means that on Intel, the instruction has a bit field in the actual instruction that says which segment register it's in reference to. And if we look at the instruction format, in that case, mov rm16 seg. So there's probably going to be this big table of that somewhere. How do we know the segment register? It's not here. Where is it encoded? I forget which table it's from, but as we can see here, it's like the register index. And the register index is, it's the register part of the mod rm byte. So the mod rm byte, The register part is the top part here. But I don't see segment registers. It's just a number. I'm sure there's a table that contains this somewhere, but don't know where it is. What if I just search for like FS here or GS? Oh man, I don't know this thing by heart anymore. Okay, well, it's encoded in the mod RM byte anyways, in the register component, and I don't know why this table doesn't, why that table doesn't tell us that, but the information is here somewhere. Okay. Looking good. Just works. Very cool. Yeah, 2B. Mov RM16 seg. UserspaceEmulator implement mov RM16 seg. Cool. There was that other one I was ignoring. Maybe I should just take care of that one. Seg RM16, because we can do that one backwards as well. It's just that's the set operation alternate mode. So we'll do a set FS alternate, or maybe a set GS alternate. We set that to 0. Yeah, let's do a set GS alternate. So that would be something like, or set, yeah, set GS. How would we do that? So we want to move EAX into not EAX, AX, 16 bits, into the GS register, and we have one input, which is the GS variable. All right. Oh, wait, did I just nuke? Not editing very well here. I probably didn't want to edit this part. Yeah, that part was just fine. There we go. Nice to get some extra instructions while we're here anyway. I mean, we could do this all day. Oh, interesting. It's complaining that the address selector is some value that it doesn't like. That's so weird. I mean, that's some validation that we have here, I guess. Read memory 32. Interesting. So it's trying to read from that selector now, and it's not one of the one of our selectors that we like, because we did set it to 0. So we do fail in memory access down the line because of that. That's funny. Let's just set it to something that we trust. So we'll set it to, what was it before? 2B, so we'll set it to 2.3. Or, dang it. Just testing that it works. And then there's a lot more work to be done on like improving the error messages and stuff that we present. No region for 23. Oh, is it trying to do a thread local variable access? It's probably that, and then it's totally messing it up because I screwed it up. Probably that's what that is. I think because I think the GS is the pointer to the thread local storage And if I set that to a bogus location, then everything gets confused. Yeah, so I probably shouldn't do that. But it seems like at least the instruction succeeded, because we can see that it's trying to read from 23 in the middle of the formatting code. So I would say it is working. Just yeah, that's good enough for me. Okay. Wait. ARM16 seg. Seg ARM16. Wait, am I not hitting this code path? Because I never implemented that instruction. I'm getting a little loopy now, like I forget. Didn't I try to use the alternate setting mode? Set JS alternate? This was supposed to use the 16-bit version. But I guess maybe it doesn't. Maybe it's not encoded in the right way. Let's find out. Let's see. So mov GS. Let's see. Never inline. Just want to see what it looks like. It has mov GS EAX. You little sneaky sneaker. That's a bit sneaky. So it's not using the 16-bit encoding. How do I get it to do that? Can I like mov? If I want to mob a short or if I want to be sure that it's 16-bit, I guess I could do it manually. If I just encode this manually, what would that be? I want to have 16 bits, and then I want to mov GSAX, right? So NASM mov. That's 8EE8. That's what we have, but it's in 32-bit mode here. So if I interpret this in 32-bit mode, then it's mov GSEAX. So if I wanted it to, if we are in 32-bit mode, how do I have to encode that? I guess I just need a operand size prefix, or a size prefix of some type. Wait, what? Bits 32, mov GSAX. Am I misunderstanding the instruction that I'm looking at? Mov seg RM16. 8E. What if I have an operand size prefix? Then what happens? Okay, I gotta go look at this instruction. Mov 8E /r blah blah blah. Move RM16 to segment register. Yeah. Okay, well, what if I hardcode a prefix on it? Then what happens? What is it, like 67? Or I forget what they are. That's the address prefix. Okay, so if I'm running in 32-bit mode and I have a 66 hex prefix before the instruction, then it will do this. Okay, so to force it to do what I want, can I do this? I forget how to put constants. It's something like this. DB inline assembly. Operand size prefix. How do I set an operand size prefix? Just go away. Surely there's some way to do something like .byte or something like that. Oh, what's the frickin' syntax? Or is the thing that I'm supposed to say mov s for like short? No, because mov is an instruction, yeah. Mov w. So mov word, could that be it? Oh man, how do you do this? That was not the right way. Okay, I need to get a little hardcode bytes inline assembly GCC. How do you do it? .byte. Oh, that was .byte. Okay. Just no $sign. Okay. Is it going to do what I want? Yes, finally, it encoded the instruction I wanted. Okay, so you can do this. Wonder if we do that anywhere in the code base. We do not. Okay. Yeah, I don't know where I've seen that trick, but I don't know how you can convince with inline assembly to use 16-bit encoding, because it's like normally when you're writing 32 or 64-bit code, you basically never want 16-bit encoded instructions. But in this case, since I want to exercise the emulator, I need it to actually make me a 16-bit version of the instruction. So I guess that's the way to do that. All right, well, that was a hassle and a half, but we are back on track. And now it fails because of that unimplemented instruction. Right, okay, so I was not being loopy, initially at least, because I hadn't implemented the instruction. Okay, and then it goes the same as this one, I think. Same basic idea, but we read a 16-bit reference instead. With the same FIXMEs applying to that one. Okay. That's probably gonna work. What were we doing with it, by the way? It was setting in an alternate way. So setGS alternate, right. It should still fail in the same way because we try to do the thread local access with the bogus segment selector, but at least we should get to that point instead of failing on the unimplemented instruction. And we get exactly that. Okay, good. So this is kind of the same as that one, I guess. MOVSeg RM16. So let's fold those together, actually. And I suppose it's a little bit tempting to make something like soft CPU write segment register, something like this, so that we can have the FIXMEs in one place. Also avoid adding too many more FIXMEs. We'll try this. So segment. What is this thing? It's a segment register. Yeah. Okay, and then something like, I mean, we can take the value with shadow here, actually. And then we do that. Bring it here. Do this. Right, segment register. Yeah, this will be nicer. So segment register and value. Don't even need the temporary. Look at us. Aren't we fancy? Okay. I just need to add that to the class here. Just put it somewhere down here. This is definitely not something you want to do outside of the thing, but internally it's a good helper to have, because then we can consolidate this error reporting here once we get to that point. Oh, this is interesting. I want a U16, but I have I guess I only need the bottom bits here. What's slice? How does that work? Slice. Forget all of the interesting tricks and template hacks that we do in soft CPU and how they work. But yeah, so here I'm reading 32 bits from memory, but I only need the bottom 16 bits. So what's the right thing to do is, I guess, to copy them out first, maybe. So then take the bottom bits only. So how do we get the bottom bits? Slice takes a member. Okay, I can't do that. But I can do this. And then value with shadow. Use 16. And then can I make it from parts somehow? Because I have both inputs. Yes, I can do that. Okay, yeah, I have the value part and the shadow part, so I'll do this. Value.value. Like this, and value.shadow. I guess it's enough to do this, now that I think about it. Would you tolerate it? You didn't. Shadow type is array. Oh, shoot. how do I do this? I forget how this thing works. Value with shadow. And the shadow is an array of bits. Is that what it is? It's an array of bytes. Shadow type, size of t. Okay, so it's 1 byte in the array per byte in the size of the value type. Okay, I can do that. I mean, it's a little bit weird, but whatever. And then I would get the shadow part here. So value dot shadow 0, value shadow 1. This is really weird. I don't think we do this in any more places though, but yeah, basically I'm constructing this thing on the fly. I think this is a special instruction though, because it's the only situation where we do a 32-bit read, but then force it into a 16-bit destination. So I don't think we need to do this anywhere else, as far as I can remember. Might be the case, but segment registers are special because they are always 16-bit. And the reason, as I was saying earlier, the reason that we want to preserve the shadow bits here is that that will allow us to complain if you do try to put uninitialized data into a segment register, because then we will have the uninitialized state here in write segment register when we eventually get to these FIXMEs, which I'm allowing myself to add today. All right, let's build. So let's see if it still runs our thing. Oh yeah, this was native execution. So does it fail in the same way? Yes, it does. Very cool. Very cool. Très cool. Okay, so I'm just gonna put a note here because this looks like a mess and a half. So, can do something like that. Actually, I wonder if it's possible to do just that. Would it swallow that? Value with shadow. Just wondering if we have this initialization pattern elsewhere. Where do these things come from? Read 16. Just looking for some code that creates one of these. Value shadow. Wait, you can create it from a U16 shadow? Wait, how does that work? T value T shadow. So I shouldn't be allowed to take this path if I have two U16s. Did I just do this in a dumb way? Because it feels like what I'm doing is dumb. So what if I static cast these to U16, just truncate, and then we truncate the shadow as value. Oh, that's what I wanted. Oh, shadow as value. Do I use that elsewhere? It's used in various places. Okay, cool. So shadow as value is what we wanted. Then maybe we don't need to do this gunk. Value shadow as value. Can we do that? Then we don't even need to explain ourselves because it looks perfectly sensible. That's much better. Okay. Yeah. It's interesting when you haven't been in a part of the code for a long time that you forget sort of you have this memory of how overall the thing works, but these little details and like, oh, the convenient way to construct the various types and things like that, all of that slips away, at least from my memory. I forget these kind of details. But yeah, we did have a more convenient way of doing this, which is good. We can say note, this instruction performs a 32-bit read, but only the bottom 16 bits are used since segment registers are 16-bit. Yeah, that's just let's just have that note at least, so that if someone's looking at this and they think, wait a minute, why are you reading 32 but then truncating it? All right, so I think we can squash this into that commit that we had earlier. And let's do a little bit of rebase magic here. So this goes into this fella, and then we're gonna rewrite it to say that we're doing both RM16 and RM32. Yep. Cool. Git stash pop, and we should be good here. And I think I'm basically happy with where we got to at this point. So I think I'm gonna call this a video. But we'll run the thing one more time. But yeah, so we implemented, what was the original problem? Push CS, right? And then we did all the other push segment. And then we did MOV in and out of segments, 16 and 32-bit encoding of the instructions. So a bunch of new instructions implemented in the UserspaceEmulator. Very cool. Don't know that these instructions are particularly popular in programs that we would want to run, but that doesn't mean that we can't support them. So that if a program would try to run these things for any reason, one area where we might run into stuff like this is there's a port of wine in the works, has been in the works for years, but once you have wine running and you might want to run like a Windows executable inside wine inside Serenity, then who knows what kind of instructions that they might throw at us, right? So having some preparation like this is pretty nifty. It would be cool to run like Windows Notepad in Wine in UserspaceEmulator someday. I wonder how far off that is. Anyways, so yeah, this is going to be the end of the video. So if you made it here, then thank you for watching, for hanging out. I hope that you saw something interesting today. I certainly enjoyed suddenly dealing with UserspaceEmulator and libx86. Once again, it's been a while, and it's good to see it again. And it reminds me that we need to make it work on 64-bit. So that's something that we have ahead of us. Anyway, thanks for hanging out. I will see you all next time. Hope you enjoyed FIXME Roulette. Bye.